Hello everyone. It is our great honor to have today Professor Karl Johansson. Professor Karl Johansson is a professor in electrical engineering and computer science at KTH Royal Institute of Technology in Sweden and founding director of Digital Futures. He earned his MS in electrical engineering and PhD in automatic control from Lund University. He has held visiting positions at UC Berkeley, Caltech, NTU, and others. His research focuses on network control systems, cyber-physical systems, with applications in transportation, energy, and automation networks. He has received numerous awards, Best Paper Awards, and other distinctions from IEEE, IFAC, and many other organizations. He has also served as on the editorial boards of Automatica, IEEE Transaction of Automatic Control, IEEE TCNS, and many other journals. Please join me in welcoming Professor Karl Johansson. Thank you.
Thank you. Thank you very much, Panagiotis. Thanks for that kind introduction. I'm delighted to be here in this seminar series. Let me just try to share the right screen now. So if I do like this, do you see the right screen or the wrong screen? Looks okay?
Perfect.
Okay.
Perfect.
Excellent. So yeah, thanks again for having me. I'm delighted to give this talk in the online seminar series on data-driven learning and control. I'm more than happy. I don't know, Panagiotis, if there could be questions or so, but if it's possible, I'm more than happy to be interrupted while I speak here. Please just let me know if someone is sending a question in the chat or so. Otherwise, I will just go on. I put this picture here. This is the main building in Stockholm in a month. That's where the Nobel Prize laureates will come and get the prize from the Swedish king. I hope to see some of you one day there. So my talk today will cover a little bit some recent work that we have been doing on machine learning for control of traffic. But before I get into this detail, let me just start with a little video here illustrating another project. Actually, we have been working in my group for 25 years now with Swedish truck industry. This is Scania, or Traton as they are called nowadays, a truck manufacturer located here outside Stockholm. And we have been working on autonomy and efficiency for these vehicles for many years. Right now, as you see from this video, one thing we are very interested in is how we can incorporate information about bad weather conditions or icy roads and so from new type of sensors in these vehicles. And you see some tests that we have been running last winter up north in Sweden, trying to incorporate this information automatically into the vehicle. So a lot is happening now these days when it comes to autonomous trucks, autonomous cars, and so on. But this is not what I'm going to talk about. I'm going to talk about, so to say, the future of this beyond current technology that is being tested and developed and prototyped. So what you see here is platooning trucks. This is something that we worked intensively on 10 years ago or so. And you see them going automated now on highways in Sweden, over the bridge in Denmark, and so on. So this is basically a technology that is available. Something that we started to think about a few years ago was when we now have this autonomous trucks, these autonomous truck platoons, we can actually use them to control traffic. If you look at the picture on the bottom of this slide, if you think about that truck, the gray truck there, typically we move a little bit slower than the cars. In Sweden, for instance, trucks goes 85 km per hour, while the cars go 110 or 120 km per hour. So which means that the truck is acting as a bottleneck for the car traffic. So basically think about it's like a fluid of cars, and the trucks is stopping it up a little bit. So the problem we got interested in is how can we regulate traffic? How can we improve traffic conditions by regulating a few autonomous vehicle, a few automated vehicle, in this case then truck platoons, in order to improve life for everybody, basically using the road infrastructure in a more efficient ways. So this is what I would like to talk about, and I will talk about some fundamentals. How do we model this? What is good, appropriate model? How do we get this model from data? And then how do we use this model to do estimation, prediction, and control? But we will start from the very basics here, because it's quite fascinating to think about that if we go back to the 18th century, fluid flows were considered by two scientists, Euler and Lagrange, that we all know about, right? And we all studied in our high school courses in physics. If you remind yourself about what Euler did when he derived his equations for fluid motion, was that he considered an intersection of a pipe where the fluid was transported, and then he derived his equation for the fluid at that intersection. Lagrange did something different. Lagrange was considered a little parcel of fluid, and then he considered what happens with that now when it evolves over a small time instance, over a small time interval delta t. And then he derived his equation of motion out of this. If we now come to traffic, none of them, as far as I know, study traffic, but if we think about traffic and traffic control technology, it's basically Euler who defines the way that we control most traffic today on highways, right? You will, I'm sure, outside Ithaca, here outside Stockholm, we have this type of traffic sensors. You have these gantries which are measuring density and flow of cars passing through. And what you also have is that you have actuation through digital road signs. So you have what you see there on the bottom of this slide here, suggested speeds, and you hope then that the driver take this. So this is somehow traffic control a la Euler. If you now think about it from a Lagrange perspective instead, so think now that instead of measuring the density and flow of vehicle at a particular point in space, we can now use floating car data. So we can use that all the vehicles more or less are connected, either through the driver has a mobile phone or through that the vehicle itself is connected. And from that information, from the actual fluid of vehicles now, we can then get information about density and flow, right? But we can also think about that we have actuators. So that truck that you see here to the left there, imagine that is automated now, or that can be remotely actuated. The velocity could be set in that truck, and in that way it would act as an actuator in this fluid. So the interesting feedback control system that we basically get out of the Lagrange way of thinking of traffic is what you see down to the right there. So we measure the information about the plant, about the traffic. We send that in to a filter, and then based on that filter, we take actions, and actions are perhaps taken by the same vehicle or by different vehicles. So this is a control architecture that we have been working on over the last 5 years or so with some students and postdocs and others continue working on this. So it's it's an interesting application if you want, and I know many of you are working on vehicle and traffic, right? So it's an interesting application, but also if you're more interested in theory and mathematics and so on, it actually poses quite some interesting fundamental problems also, because it's seldom in control theory where we have sensors and actuators moving in the actual plant that we are controlling. But this is basically what I'm showing to you here, right? So again, let me just repeat. So what we have is that we have a number of connected and autonomous vehicle. They are measuring the density and flow around them. These measurements are then incorporated into a model that we are learning out of that data. That is a model of the traffic. And then this model is used in order to now reconstruct and predict the state of the traffic. And then based on that prediction, we then control the action of these red vehicles. That could be the trucks that I showed you earlier. And in that way, we try to regulate the traffic in a better way. So that is, so to say, the system that we are going to now discuss a little bit more into detail what we are doing. So in order to do that, we need to look a little bit into the very basics of traffic models. And to a large extent, you can say over the last 100 years or so, it's been dominated by two types of models. One type of model are microscopic models. In the microscopic models, what we have is that we model each individual vehicle. You see it's like a dot here, right? So over a road of length L here, we have a number of such vehicles. The other extreme, so to say, the other type of model that we have is called macroscopic traffic models. In these models, we forget about the individual vehicle. Instead, we represent vehicles through their density over this road segment. So the density rho here is a function of the position along the road and time. And we in this case, as you see, I say that the density is high, then it's close to 1. The density is low, it's close to 0 in this particular case. So these two fundamentally different models give rise now to different mathematical model also. So in the first case, you would follow Newton, right? You will model each individual vehicle through the Newton mechanics, saying that the velocity of the vehicle is given by some map here, v, that for instance could depend on the density that we have at that point. While in the macroscopic model instead, we will use a partial differential equation. So in this case, the partial differential equation describes how the density rho depends or evolves with time and space. So it's kind of a conservation law that we have there. And in traffic theory, this is called LWR model from the authors who come up with this in the 50s. So in the PDE model here, you see there is this function v, which is the velocity that we have given a certain density. So this in traffic theory is defined by something that is called the fundamental diagram. So in theory, that diagram looks like the picture up to the right, where you see we have traffic density on the x-axis, and then we have traffic flow, so rho times the velocity on the y-axis. And you see if the density is small, it grows linearly, the flow with the density, up to a maximum, and that maximum is the maximum capacity of the road. If then the density of vehicle grows further, this is going to decrease like that. So this was a 1-minute crash course in traffic theory and two of these classical models. This is not just theory. Actually, this macroscopic traffic model is quite accurate also in practice. So if we go to some experiment we did 10 years ago here outside Stockholm from that type of measurement devices that I showed you earlier. So we just over a few weeks measured the density and flow that we had at different sites on the highway here. We get the diagram that you see to the top right. And you see that for low densities, it follows this linear characteristic that you saw that it should do theoretically. If you have high density, we are all over, and this model is not very accurate. But it kind of illustrates how with this model we can imagine that we can use it for observations, for predictions, and for control under certain assumptions. But let's come back to the problem now that I was posing earlier. So what we are interested in is to control and sense a number of connected autonomous vehicles along this highway. So basically, out of what I talked about up to now, these two type of models, you see that what we have in this case is that we have an interconnection between these models, because basically the traffic flow is given by this PDE equation. And then we have a number, in this case capital N, number of connected and autonomous vehicles. So what does this mean mathematically? It means that we have an interesting object now, because we say that these red vehicles, their velocity are given by something that we are steering. But of course, they are influencing the partial differential equation that I have on top. So researchers, mathematicians now have been studying this. When do we have solutions for this, and so on. So it's an interesting mathematical object to analyze. But also from a control viewpoint now, this is interesting. How should we control these individual vehicles so that we achieve what we want? In the talk later on, I'm going to show experiments and so on, where we illustrate how the density is evolving over time and space. So please look at the diagram here to the right, because we will look at several of them later on. So in this particular diagram, we have time on the x-axis and we have position on the y-axis. In black there, I have indicated the red vehicles. So these are the probe vehicles which is passing through the road with different velocities, right? But you see that they are moving as time goes from 0 to 2 hours. They move then in position from 0, 1, 2 kilometers, etc., right? Then you see that this space is colored, and the color represents now the density of vehicles. So in this particular case now, more reddish color means that it's high density. So vehicles are moving slower in this case. So this is, so to say, the object we are going to consider. So now, based on this, what we are interested in is, out of the probe vehicle, we would like to reconstruct a model of the traffic. So if you allow me to jump back to the previous picture, so what I'm saying is that out of measurements taken by these black lines, now these vehicles that travel there, the question is, can I reconstruct the color of all over this space that I have? I assume now that I can measure around each vehicle, but can I extrapolate or interpolate in between vehicles? Of course, if we have too few vehicles, this is impossible if there is too much changes happening in the density. But under certain circumstances, it could be interesting to see if this works or not. So mathematically, how do we formulate that problem? So this is what we will do next now. So what I have here is, first in the red rectangle there, I indicate what information I assume that every red probe vehicle gives me. So each probe vehicle gives its position x, the density around it. So we assume that the vehicle can look around itself and tells what are the density of vehicle around it, and then the velocity that it has. So it's reasonable data to assume that each vehicle here can actually obtain. And then out of this data from a number n of these vehicles, we want to reconstruct the density everywhere in that space. So what does it mean? So we would like to find a density rho hat star, which minimizes now this optimization problem. So this is now the density rho that we have obtained from the measurements minus now some estimated density. So we would like to find rho hat, which should be now close to what we are getting out of the data. So that is a learning problem or an optimization problem that we are going to formulate a little bit more precise next here. So since it's so popular these days with neural network and machine learning, of course, we formulate it as such a problem. So what we do here is that we introduce two neural networks. So one neural network is the map from time and space to rho. So from t and x to rho hat. So the estimated density everywhere. It's parameterized with the parameters of the neural network. I call it theta rho. So this is one neural network. The second neural network is basically the fundamental diagram. So I parameterize another neural network with theta v, which is a map now from rho to the velocity v. So when I now want to train these two neural networks, it's very natural to formulate the optimization problem you see on the bottom of this slide. So we want to minimize the discrepancy between the measured rho and the estimated rho, and the same thing with v and the estimated v. So this is maybe if you studied machine learning first course, this is what you would do, and you will plug it into one of the tools and you will run this, and it won't work. You wouldn't be able to get good results if you do that. Why? The reason why is that you didn't put any constraints or any prior on that rho here should actually be a density that is fulfilling that partial differential equation. It should be a fluid of cars, right? And nothing here in the formulation tells that. So what one then can do is that one can add that physical constraint to the formulation of this machine learning problem. So let's do that. So we add now the physical constraint, so the PDE that I brought up earlier, right? So the rho hat here should fulfill this PDE. And then I want also that fundamental diagram should have certain properties. So I put the constraint also on the function v there, that neural network. And then I now run my data-based learning. So this is something which has been formulating in this way, has been quite popular the last few years, not only in traffic, in many different areas. There is papers by a group in Brown. They coined the term physics-informed neural network, PINs, for this, and then it's been applied in many different science area and engineering areas. We applied this early to traffic modeling along the line of what I'm talking about here. But let's move on now and do the actual computations, and let me show a little bit more into detail what it looks like. So we trained the parameters of the two neural network, the theta rho and theta v, by now minimizing a cost function like the one you see here, given now the physical constraints. If we should do this in practice, we typically do a Lagrange relaxation, right? We move up the constraints to the cost, and then we introduce some hyperparameters. In this case, they are called lambda rho and lambda v, and then we get the minimax problem to solve. So how can one solve that? It can, for instance, be solved by doing primal dual decomposition of the problem. So we have a primal problem where we would like to find the parameters of the neural network, the thetas, and then we have a dual problem where we are now finding these adjunct variables lambda rho and lambda v. And this can be done by, for instance, doing primal dual gradient descent iterations where one first do a step in theta, and then you do a step in lambda, and then you go back and so on. So I won't go further into the details, but if you're interested in this and so on, there are different numerical algorithms and so on for running this, and there is also something which I won't touch upon here, which is very important to get this to work, is how to sample the data here for when you run these things. But let's instead see how it works. What is the quality that we get out of this? So let's now run some experiments. Experiments in this case means sumo simulations. So here I run individual vehicles over a highway stretch. In this case, 2.5 kilometers over 7 minutes. And then I take the data from all these vehicles and I compute the density that I have over this segment, and then I plot it here. So again, the color here indicates now what is the density of these vehicles when I run these particle simulations. The black curves here again is then the probe vehicles. So remember that out of these probe vehicles, we now would like to find out the true density in between the vehicles. So we do that using the technique that I just explained. So we basically now use this model and we look at what is now the density that we obtain. And as you see here now, in between the black curves, the color coding is quite similar in the estimation or reconstruction to the right compared to the true data to the left. It's not perfect. You see that it's a little bit more shady to the left, but it's pretty good up to this 7 minutes. What I then do after 7 minutes is that I continue running this model. So I run this model now for 2 more minutes, and you see this is the way I can now predict into the future the evolution of the traffic. Of course, I don't have any information from the probe vehicle about the future there, right? So this is just open loop prediction in this particular case. So let's look a little bit more into the data of how these neural networks actually, what is the result, so to say, out of this neural network. So let me remind you that we were training 2 neural networks. One was a map from T and X to rho. So that is, of course, exactly the color that you see there. So it's exactly that map, right? From the X and Y axis to the color of this picture. That is one neural network. That is this map that you see. The other map we were training was the map from rho to V, right? So if we plot that, you get this blue curve to the right here. The black dots there are the actual measurement data that we have. So you see we get something where the velocity decrease with the density. We can now, of course, instead of plotting velocity here on the y-axis, we can plot rho times velocity. So we get the flow instead. And then you see that we get again that shape of the fundamental diagram that you have seen before. But in this case, we have obtained that by training on the data that we got from these individual probe vehicles, and then we obtain this automatically. So it seems like it's working pretty well. Let's now turn to using this, and let's use it for that type of control that I described earlier. So in this particular, I will only describe, so to say, the simplest type of control you can think about. So in this case, to the yellow here to the right, you see here we have high density, and then we have a track platoon or a track here to the left, this blue thing, right? So what we now are doing is that we are regulating the velocity of that track platoon and try to adjust it so that we minimize the traffic jam over to the right. That is the problem that I described earlier. And let's see in this type of numerical evaluations now what that looks like. So again, you have a picture where the density of the cars are illustrating with the color coding. In this case, yellow mean high density. So we have after 50 kilometer here, you see that at time t0, we have maybe an accident or so, and you see its high density is built up and it's propagating backward in space and forward in time until it's dissolved after some time up here, right? If we now run our track platoon, the red curve here with constant velocity, you see that it keeps the constant velocity until it gets into this congested area. Then it slows down and travels through that area and then continues with the same velocity that it had previously. So this is just illustrating what is now happening if you drive such an actuator in the flow of vehicles. So let's now do active control. So what is active control of this track platoon? What does it mean in this case? So we can interpret that in the fundamental diagram, because the track platoon, as I said earlier, will typically now go a little bit slower than the cars. So it imposes a constraint on the car velocity. This can be interpreted in the fundamental diagram. It basically means that going from the blue fundamental diagram where we didn't have any track platoon to the red one where we have a track platoon with a certain speed. So we are basically reducing the capacity of the road, and we can interpret that now in this fundamental diagram. So now we can control the velocity of the trucks in such a way so that we somehow maximize the efficiency of this moving bottleneck when it comes to minimizing the congestion or traffic jam that we had due to this yellow area that we have. So you see in the second plot now, the plot to the right, the velocity of the track platoon is slightly lower than in the left curve, in the left plot, as you see. And then you see we hit, so to say, the congested area exactly when it's being dissolved. How comes that it can be dissolved? It's because that the track platoon is slowing down the cars a little bit, right? So if you look behind the track platoon, so the area up here, you see that that is a little bit bigger than the area that we had in the left plot. So we have basically slowed down a few vehicles. We have increased a little bit, if you want, the congestion behind the track platoon, but with that we actually avoid such a big congested area. So a very relevant question now is, when slowing down this vehicle, will this mean that I in total slow down all the total of vehicles? So if I sum up the travel time for all vehicle in such a scenario, and the answer is no. It's actually a social benefit of this. I won't go into the detail here, but we have been showing that in a number of papers as well. So this is a way, so to say, to make something social good, in the sense of that the average speed, the travel time is actually reduced thanks to this type of traffic control implementation that I showed. For the last few minutes now, I'm going to talk about another way of doing this type of observer and estimation, another type of machine learning model. So in the previous part, I talked about this physics-informed neural network and so on. So let me just take a few minutes showing something which is a CDC 2025 paper that we will present in a month, which is using a different techniques And I think this could be interesting also to compare with and so on. So in this case, you see that the basic setup is the same as previously, right? So we have the traffic of vehicles here. I, in this particular case, assume now that I can sense the density, not from specific vehicles, but I can sense the density at a particular point in space. So these are the points X here, which are indicating that I measured at some y x of t here, the density. And then I feed that into an observer, these measurements that are taken at particular space instances along the road. And then I use a model that I will come into a little bit more in detail that I have trained now based on some other data that I have, some prior data that I have been learning a model similar to what I talked about before. And then I use these together in order to get an estimate rho hat of the density, which I'm using then for control of the traffic. So there are two pieces in this that I would like to go into a little bit detail now. So what does the prediction operator, this guy, what does that look like? And what does the observer in this case look like? So let's go into a bit this prediction operator. So this is, as I said, a fundamentally different approach than previous approach. So this comes from something called Fourier neural operator. Again, perhaps some of the people in the audience have run into them. So they have been developed by various research groups, particularly Anand Kama from Caltech have developed that for a number of different applications, and also some fundamental theory around this. So this is not now, that the crossover means here, so this is not now a finite dimensional neural network any longer. We are learning an operator directly, and this operator is defined in the Fourier domain. So instead of having basis function that is defined by a regular neural network as we had previously, instead we defined now basis function, which is basically frequencies, which we are now training the parameter of from the data that we have obtained. So we have data from densities, and then we are now training these neural operators, and then we can use these neural operators to do predictions. Since our data is in the Euclidean domain, and we want the prediction to be the Euclidean domain, of course we need to do some Fourier transformation and some inverse Fourier transformation here. But so to say, the computations are really done in the Fourier domain, and these type of operators have some very nice type of properties for predictions and so on. This is what we are utilizing now for this particular application. And then we take now these operators and we put them into an observer. And this observer now is described by this closed loop diagram, which I would like to describe a little bit further. So the prediction operator is this block that I call predict here. So this predict is now trained with some data that I have obtained perhaps from vehicles or from else. So I obtained that prediction. I use that to now get a first predicted state estimate p hat. Then I take the data that I obtain from these fixed sensors that I talked about, and I use the data from these fixed sensors, and I use that and look at how off are these database state estimate from the one that I got from that prediction I get from the neural operator, and then I get an error term, and I use that error term to get the correction of the prediction and an updated prediction called p hat u. And then that is fed back into the prediction, and this is then a closed loop observer. So it's very similar to the classical Leuenberger observer or other observer where you have a correction term and where you use that correction term to update the prediction. The difference now is that the space we are working in is different from the usual maybe state space of a dynamical system. So it's a higher order space that we have. So how does this work in practice now in similar setup as the one that we talked about before? So again, we go back to sumo simulators. We have this type of diagram that you have seen previously. So out of the sumo simulations, we compute the density and the density over time and space, and we get these colorful plots. Let me indicate here again what I've said a number of times now. So in this setup, we assume that we have these fixed gates where we, every kilometer or so, can get the density. So these are indicated now by this black solid line going across here. There, at this point, we know the densities. So what happens now if we run this? So the true is now to the left. So let's say that we don't care about this feedback observer that I introduced, but we just use prediction from that neural operator that we have trained. Then we get something that looks like the picture to the right here, or the plot to the right. So you see that in the beginning, the first few minutes, it looks quite okay, but then it becomes unstable and we are all over. So just doing prediction with this open loop observer doesn't work. Over short time instances, it works, but you cannot use it consistently because it's unstable. You can do an ad hoc solution to that. You could reset the estimate periodically, right? So you can do this open loop observation and then you reset it and then you predict again from that point and you reset it and so on. In this case, it will be stable, but as you see there to the left, it doesn't give us consistent predictions. If we now run that type of architecture, this closed loop observer that I introduced, then you see we get something much better than in the other cases. You see that it's still not perfect, it's still not exactly what we have in the true, but it looks a little bit better than in the other. So we both have consistent predictions and we have stable behavior. We can now vary the certainty of the data here to check what happens. So in the left case was the perfect situation, no noise on the data. If we add noise now on the data, you see that the error that we get with our method is a little bit bigger than in the non-error case, but it's doing much better than the other two cases. When we do machine learning, one often compare with something called out of distribution data. So you take data now that doesn't have the same distribution as the one that you train with. And also under these circumstances, you see that we are robust to that type of disturbances. And as I said, in our case, this closed loop, as well as with the open loop we reset, we're able to have a stable estimate, which is not the case otherwise. So with that, I would like to wrap up, and I hope we have time for some discussions and questions. So what I talked about here today is how we can use individual vehicles to regulate car traffic. I argued about it using trucks. It's not only because we have been working on trucks for a long time, but it also trucks are driven by professional drivers, and the technology for automating trucks is easier to do. A truck costs more money, and also it has more advanced technology usually than a car. So today a modern truck, for instance, that we are experimenting with, we have a GPU on board and so on. So there is a lot of computational capability and so on. And therefore, I think this is a very relevant problem to think about. We propose a particular control architecture for actually learning traffic models from data from individual vehicles. And then I show two different approaches to build estimators on that type of data. One builds on pins and the other one on Fourier neural operators. Let me also say two things I call extension here. So I didn't talk about implementation, but as you can imagine, we want to do these things fast. So one relevant problem, and we also have another CDC paper on that, is how do you get real-time implementation out of this? How can you run this iteratively and fast enough so you can actually use it for controlling traffic? So that is one important aspect where I think also more work needs to be done. But also, let me highlight, now we talked all about traffic here today, but similar approaches where we have plant dynamics, process dynamics, which is not just a linear ODE or a nonlinear ODE, but more complex type of dynamics like PDEs and so on, pops up in many different areas. And now with new techniques, one can actually model them and build data-based models combined with physics model. And we have been doing that in a few different areas. And we are quite excited both building control theory around such framework, but also implementing and testing it in practice. So with that, I would like to thank you very much for your attention. And I hope we have some possibility to discuss now. So thank you. Thank you so much.
Thank you very much, Professor. We have some questions. First, on slide 14,
Yes.
how do you guarantee no duality gap between the primal and dual problem in your training of the physics-informed neural network?
So yeah, that's an excellent question. So to say to have a zero gap there, I mean, you need some convexity properties and so on to hold in general for this gap to be zero or to be controlled. With this model that we have here, so with this PDE, actually the second order PDE model here, we cannot theoretically prove that this is going to converge or that we will have a zero gap in this iteration. But under certain assumption and so on, one can make guarantees. But in this particular implementation I was describing here, unfortunately, there is no such general guarantee more than under certain further assumptions that I didn't go into here in detail. Thanks for that question. Thank you.
Thank you. The next question is, could you elaborate a bit more how error can improve the prediction with the neural network?
The question was about the last part I talked about, or is that? I think you are muted now, Panagiotis.
Yes, I can repeat the question.
Yes.
Could you elaborate a bit more how error can improve the prediction with the neural network? And yes, it's the last part that you said. Yes.
Yeah. So this is, I mean, this, so to say, the way we describe it here in this observer is a new way of describing it. As I said, it follows the principle of classical observers in the sense that we are comparing now measurements. In this case, measurements comes from this YM, from these stationary sensors, and they are then compared with what the prediction is. But notice that different from a traditional Leuenberger observer, the prediction should give the density over the whole space. So therefore, we need to interpolate the measured data so that we get an estimate over the whole space, and then we compare that database state estimate, that's called here p hat d, with what we get from that prediction. So this means now that we get an error all over this space, right? So this is the E hat. So E hat is basically a 2D map also in this case. So a map that goes from the location, the X location and the time into the space of densities, right? And then we are comparing that with what we predicted originally. So that will then provide a correction term to that. And then we are feeding that back into the original prediction that we had. So this is how it works in that sense. I don't know if that answered the question. Then of course one need to go into the algorithm for the correction now of the neural operator. So here in this talk, right, the neural operator is what I represent as the G here. So I realize, of course, that I didn't describe that in mathematical detail, what that is and how that connection is being done. I'm more than happy to do that in more detail and to send the paper of anyone who is interested in that. But so to say, on the high level, this is the correction that is happening in this case. Yes. Okay.
Thank you very much, Professor. I don't have any other questions.
Can I ask a question?
Yes.
Yeah. Hi, Dr. Johansson. I have a big picture question. So I'm not that familiar with traffic theory. So when it comes to the fundamental diagram, what factors sort of affect the exact shape of the fundamental diagram? When you introduce the track, the shape sort of shifted down, and do road conditions, maybe the geographic location within the country, and all sorts of factors. How is the shape exactly determined, or what does it depend?
Yeah, thanks for that. Thanks for that question. Maybe I start sharing again. I think so. Let me comment a little bit. Maybe I should comment a little bit more on the fundamental diagram in general, because you see, so as I said, this goes back a long time when people introduced this type of models, and in the literature, I mean, you can go to conferences in traffic and they talk about different ways of estimating this or doing, different part of this. And one thing to start with, before I answer your question, Nishan, I would like to just highlight one thing, that in traffic, there you can consider it as I do it in this talk, that the fundamental diagram is basically describing properties of one road segment. But that is a very basic way of doing it if you then will talk with traffic experts and so on who would work on that. Because they use also this when you look at a part of a city or so. Then you also have the fundamental diagram basically describing not how you can drive on one road, but basically how you drive through a certain part of the city and the density of traffic in that city and so on. I just wanted to say that first, because that is important here, because notice when I talk about now modeling this road segment and using it, I basically use that model as a way of translating data into a way of doing control. So notice that in this particular way work, this is the only thing I'm doing. I'm getting data from the vehicles, and then how should I incorporate that in a control algorithm? Okay, I do that by actually estimating that diagram, and then I incorporate it into the control because I talk about that I change the shape and so on. So now you can ask yourself a couple of questions. One is, what are reasonable shapes of this diagram, and what is physically relevant here. And I didn't at all give you any details on this, but let me just give you a little bit an appetizer. If the density is going down or the density is going up, it's not at all so that you follow necessarily this type of curves. You might actually have jumps in the diagram, as you can imagine, right? Because if you are actually accelerating or if you are deaccelerating, it will not be so that all the vehicle around you are going to follow your change, right? And you know also that if you slow down, necessarily the vehicles behind you will slow down, otherwise they run into you, right? You can speed up if there is no vehicle in front of you. So you see that the way the fundamental diagram, in my view, it's like an abstraction that you can reason about certain physical properties, but one have to be a little bit careful when one translates it to any type of control or any type of model here. So, but there is in any traffic theory textbook, you will see, so to say, a chapter on this and a discussion and so on. But that's kind of, I just wanted to illustrate a little bit this. I don't know if I answered your question now, but at least elaborate a bit.
Yeah, definitely. Thank you so much.
Thank you. Thanks.
Thank you very much, Professor. I have another question. Could the traffic density estimation and flow control be implemented simultaneously in an online manner?
Absolutely. I think that's that's really why I like giving these talks, because you see, my presentation here, I want to stress that is not telling, okay, this is the way that we are going to control traffic now the coming 50 years or something like that. I think that I really see this work that we are doing as opening up a number of different type of new questions of how control can actually be done. So now you can ask exactly the question you were asking. So could we now, directly based on data that I have around me as a vehicle, maybe one vehicle or maybe a few vehicles around, could we actually implement something which is along the line what I talk about here in such a distributed or semi-distributed way, using just data directly and control the vehicle? In this case here, notice that what I presented is a very centralized type of structure, right? I say that vehicles now propagate their information into a central model, and then I do the computation for the control based on that model, then distribute it out. So this is kind of, as you know, in centralized control versus distributed decentralized control, it's kind of often we start with the centralized, and then we can reason about how we can distribute it and so. So I think this, what you say there, is very, very relevant, and it's an interesting direction. And you can think also like another way of reflecting on your question is to say that, you know, today our traffic system, by actually indicating changes in the velocity by digital road sign or something like that, right? That is a way of distributing. The system is distributed, right? Action is taken by drivers. Drivers take information from the digital road sign and from other vehicles into account. So we know that the system can be controlled in a distributed way. The question is just if we do it in an automated way, how would we get a good model of the traffic around, not just what the vehicle, how the vehicle in front is driving, but actually some sort of property of the traffic around us. So that would be the challenge. But in principle, the important information is ahead of you, right? So you would like to have information further downstream, propagating upstream, so that vehicles who might now get into congestion slow down a little bit earlier. And that seems to, from a very practical viewpoint or intuitive viewpoint, seems to be perfectly fine to implement in a distributed way, right? So So yes, I think very well one can do this distributed, and one can do it without separating the estimation from the control. But both these things are not at all obvious how to do. So we need to, so to say, develop the control here in a step-by-step way, I think.
Thank you very much. I don't have any other questions in the chat. So thank you very much once again for this excellent seminar.
Thank you. Thank you all for coming. Thank you. Okay. Have
Thank
a
you.
good day.